This will be better. All right. What's the first thing you did with this problem? You drew it. I love it. You knew that because I populated drawing it. Great way to get an easy point. Okay? A system has 4 energy levels uniformly distributed at 3 times 10 to the negative 20th joules apart. Let ground state be 0. Does this line need to be here for you to know to write that the ground state is 0? No. That could be missing, and you would still know to write 0 energy as your ground state every time. Okay? The populations of the energy levels are given by Boltzmann. This is the clue to go ahead and use the probability and partition function equations for Boltzmann that you've learned. Even if these things weren't evenly spaced, you can still apply those equations, right? It's not gonna be a perfectly like exponential decay up through all of the levels. But even if they weren't evenly spaced, you would still use those equations. They're still valid. Okay? So the relevant equations you can use, identify what you can use. Okay? Identify everything you know. T is 298 Kelvin. Okay. Do I have N or N sub J? What are my weighting factors? They're all 1. There's absolutely nothing to suggest they're not 1 here. Okay. The words given by Boltzmann are not necessarily the clue that they're 1, because like I said, using these equations with Boltzmann factor are relevant even when they have weighting factors involved, okay? But there's nothing in this information for them to be anything other than 1. What fraction of the particles are in the ground state? So what is it asking me for? Yes?
What would the wording be that would
It could look vastly different depending on the nature of the problem. It could be something like, you know, let the end units on the trans double bond be the same such that there's, you know, every configuration looks the same. There's 2 different ways to be bent, something like that. Again, try the homework.
So for the 6, it would be 2, like 2.
This is 2, okay. Yep. Weighting factor was 2 for our, I should have drawn these like going up, but yes, it was 2 different ways. And the language will say something like, there's more than 1 way to be this type, you know. But exactly how I'll phrase it, you'll have to read. Okay.
The phrasing populations of the energy levels is just like referring to the probability
yes.
of it being an energy level, not the degeneracy.
Yes. Yes. The populations of the energies are given by, that's probably, the word is meant to be probability, like how they're occupied, the likelihood they're there. Okay, so what is it asking for in this first one? What variables is it asking for? I mean, it's technically asking for P sub j. What fraction of the particles is kind of a weird phrasing, but a fraction would be the number in the ground state over the total number. And the fraction of the particles in the first excited state, 25C, is the same as 298K. All this does for me is make sure I don't have to do partition function twice for 2 different temps. If these were different temps, you couldn't use the same partition function twice. And in this one, it's asking you for the fraction of the particles in first excited state, so n sub 1 over n. This was some notation that I did show last time on letting beta be this whole term 1 over kBt, just to keep things neater when you're writing out your work. It's total, this should be raised to the 20th. It's totally up to you whether or not you want to use this type of notation or whether you want to write your numbers in every single time, whatever's easier for you. When you're doing your calculation, you still have to type them in. So you know, whatever makes it neater for you. But what you could do is then set this here and set up your partition function like this. Okay. Weighting factors, G sub j are all 1. Okay. And this is 0, they're evenly spaced, so I've let epsilon be the spacing, 3 times 10 to the negative 20th joules. Again, to just make this look neater. Totally up to you, it's optional. Just as long as you know what you're doing and keeping track of things on your own. Okay. So then the next state is going to be, you know, 1 times epsilon, 2 times epsilon, 3 times epsilon. They're all times beta, which is 1 over kBt. We know that's in the bottom of our Boltzmann factor for all of these. So Q is equal to 1 plus E if you plug all of this in and do the math, to the negative 7.29, E to the negative 14.69, E to the negative 21.885. Partition function is 1.00068. These are really small numbers. Even this is a really small number, okay? As the energy levels get bigger, they start contributing to partition function negligibly. Eventually you could go, nothing's in that level. Even though it exists, the probability of being there is so low, it's essentially 0, okay? The first term pretty much carries everything in partition function. So for the ground state, now I'm using my probability calculation, okay, which is Boltzmann factor on the top, but in this case for the 0th state, it would be this whole term here, but it's 1 times e to the negative 0, it's just a 1 over partition function, 0.9993. For the first excited state, we have our next term. The 1 is gone again, but here's my weighting factor is here, okay? It's 1 e raised to the negative 3 times 10 to the negative 20th joules over, put in everything, plug it all in, 0.00007. Those are the answers to this problem. So then what is the probability of being in the second energy state? 0. If you add these two numbers together, you have hit 1. I don't know if they're rounded, I don't remember, but it's essentially 0, right? Any questions about that? All right, let's take a break.